So this is our laboratory report for experiment M1, resistivity measurement of semiconductor by 4-point probe method. The group's members were Kasrina binti Abdul Latif, A24SC0306, Rankistina binti Jailani, A24SC0274, and Putri Naraoni binti Azamuddin, A24SC0303. The date of the experiment was 29th April 2026, and the lecturers in charge was Dr. Nur Hafizah Hasim. The aims of the experiment were to measure the resistivity rho of the semiconductor materials by using 4-point probes and to determine the energy band gap EG of the semiconductors. The apparatus used in this experiment were probes arrangement, GE sample, oven, 4-probe setup, and thermometer. This is some of the theory that related with the M1 experiment, and the values of certain transistor parameters, such as the equivalent base resistance RB, are at least linearly related to the resistivity of the material. The resistivity rho may be calculated for various temperature using the Arrhenius equation. And then the equation 1.1, which is rho equal to rho naught exponential in bracket Eg over 2kBt. And then, if the sample of the semi-infinite volume and the interprobe spacings are equal, it can be shown that the resistivity of the semi-infinite volume is given by rho equal to 2 pi s in bracket V over I, which is the equation 1.2. This is the two figures that showing the experimental setup. The figure 1.1 shows the experimental setup in physics laboratory manual, while the second figure is showing the experimental setup in the laboratory.
For procedure, first step, the sample germanium was put on the base plate of the 4-probe arrangement. The pipe holding the 4 probes was unscrewed and let 4 probes rest in the middle of the sample. Pressure was applied very gentle on the probes for proper electrical contact. Second step, the outer pair of probes, red or black leads, were connected to the constant current power supply, and the inner pair, yellow or green leads, to the probe voltage terminals. Third, the 4-probe arrangement was placed in the oven and the thermometer in the oven trough. The hole provided was fixed. Next, the AC mains of 4-probe setup were switched on and digital panel meter in the current measuring mode was put through the selector switch. In this position, LED facing milliampere would do. The current was adjusted to a desired value, say 5 milliampere. Next, the digital panel meter was put in the voltage measuring mode. In this position, LED facing millivolt would glow and meter would read the voltage between the probes. Next, the oven power supply was connected and the oven was switched on. The measurement for increasing temperature was recorded. Next, the distance between probes S and the thickness of crystal W was measured. Lastly, the oven was switched off and the voltage for decreasing temperature were recorded.
Next is going to be the analysis part, which is consists of question and answer, discussion, and also the conclusion. Question 1. What is the advantage of the four-probe method over other conventional method? The four-probe method is preferred for measuring the resistivity of semiconductors because it eliminates the effect of contact resistance and also the lead resistance. In a conventional two-probe method, the measured voltage includes the voltage drop across both the samples and the contact points, where it actually can introduce significant errors. In the four-probe method, current is supplied through the two outer probes while the voltage is measured across the two inner probes. Since the voltage measuring circuit draws negligible current, the measured voltage corresponds only to the sample resistance, resulting in more accurate resistivity measurement. Question 2. Can we use an ordinary millivoltmeter instead of an electronic millivoltmeter or potentiometer to measure the inner probe voltage, and why? So the answer is no. An ordinary millivoltmeter should not be used because its input resistance is relatively low, causing it to draw current from the inner probes. This additional current alters the potential distributions in the sample and leads to inaccurate voltage measurement. An electronic millivoltmeter or potentiometer has a very high input resistance and therefore draws negligible current. As a result, the measured voltage accurately represents the true potential difference between the inner probes, ensuring precise resistivity calculation. According to the four-probe measurement principle, the voltage measuring device should ideally draw no current so that the measured voltage is not affected by the measuring instrument itself.
This is the calculation for temperature increasing. This is the graph ln rho versus 1 over T for temperature increasing. This is the temperature decreasing calculation. This is the graph for ln rho versus 1 over T for temperature decreasing. Then 3 asks to calculate Eg from the curve by centroid and least square method LSM, and the photo shows is the calculation for LSM and the centroid for increasing temperature. And for decreasing also, we have calculate the centroid and least square using the least square method. To explain the behavior from the graph we have already saw just now, the behavior of the graph of ln rho versus 1 over T for both increasing and decreasing voltage, the slope is upward. And for the Eg value for increasing temperature is negative 3.93 eV, and for decreasing temperature, the Eg value is 5.34 times 10 to the power of negative 7 eV. 4. Calculate rho naught and explain why a semiconductor behaves as an insulator at 0 Kelvin. For temperature increase, the rho value is 5.57 times 10 to the power of 25 ohms meter, and for temperature decrease, the rho naught value is 0.035 ohms meter. And why semiconductor behave as an insulator at 0 Kelvin? Because semiconductor is a material that has spatial behavior due to temperature change. The conduction will increase when its temperature increase. Pure semiconductor materials are more important to current resistance in room temperature because it have an energy gap much larger than the conduction metal but very small compared to the resistant materials. More electrons will gain enough energy to promote themselves from the valence band into the conduction band toward the positive end when temperature increase. If semiconductor materials temperature drop to 0 Kelvin, it will behave as an insulator due to no electron was able to cross the energy gap because of the absence of kinetic energy.
So I will be continuing to the next part, which is the discussion. The objective of the experiment was to measure the resistivity of semiconductor using the four-probe method and to determine its energy band gap, Eg. The experiment was successfully carried out by measuring the voltage across the inner probes while a constant current was supplied through the outer probes. The resistivity of the semiconductor was then calculated at different temperatures, and the relationship between ln rho and 1 over T was analyzed. The four-probe method was chosen because it provides more accurate resistivity measurement than conventional two-probe methods. In the two-probes method, the measured resistance includes the contact resistance between the probes and the sample, as well as the resistance of the connecting leads. This additional resistance introduces errors in the measurement, In contrast, the four-probe method separates the current-carrying probes from the voltage-measuring probes, effectively eliminating the influence of the contact and also the lead resistance. Therefore, the measured voltage corresponds only to the resistance of the semiconductor sample, resulting in higher accuracy. The experimental result shows that the resistivity of the semiconductor decreases as the temperature increases. This behavior is characteristic of the semiconductor and is opposite to that of metallic conductors. As temperature increases, more electrons gain sufficient thermal energy to move from the valence band to the conduction band. The increase in charge carrier concentrations lead to an increase in electrical conductivity and consequently a decrease in resistivity. The graph of lone rho versus 1 over t produces a nearly straight line that confirming the theoretical relationship rho equal to rho naught exponential the fractions of Eg over 2 kBt, or lone rho equal to ln rho naught plus Eg dot 2 kb over 1 over t, where k is the Boltzmann constant and T is the absolute temperature. The linear nature of the graph indicates that the semiconductor follows the expected temperature-dependent conduction mechanism. The slope of the graph was used to determine the energy band gap, which is Eg, using both the centroid method and the least square method LSM. Any difference between the two calculated values may be attributed to experimental uncertainties and data fluctuation. However, the least square method generally provides a more reliable estimate because it uses all data points and minimizes random errors. An electronic millivoltmeter or potentiometer was required in this experiment because the voltage developed across the inner probes was very small. This instrument possesses a very high input impedance, ensuring that negligible current is drawn from the voltage probes. If an ordinary millivoltmeter were used, it would draw current from the circuit and alter the measured voltage, leading to inaccurate resistivity calculation. The experiment also demonstrates why a semiconductor behaves as an insulator at absolute zero temperature, which is 0 Kelvin, and at this temperature, there is insufficient thermal energy to excite electron from the valence band to the conduction bands. As a result, the conduction band remains empty, no free charge carriers are available, and the resistivity becomes extremely large. Therefore, an ideal semiconductor behaves like an insulator at 0 Kelvin. Some sources of errors in this experiment include fluctuation in temperature during measurement, improper probe contact with the sample surface, instrument inaccuracies, and errors in reading the voltage value. These factors can affect the calculated resistivity and also the energy band gap values. Despite these limitations, the experimental results were consistent with semiconductor theory. In conclusion, the objective of this experiment were achieved. The four-probe method successfully measured the resistivity of the semiconductor, and the energy band gap was determined from the temperature dependence of resistivity. The observed decrease in resistivity with increasing temperature and the linear relationship between ln rho and 1 over t confirm the expected behavior of semiconductor materials.
For conclusion, the energy band gap for decreasing temperature and increasing temperature are 5.34 times 10 to the power of -7 eV and -3.93 eV respectively for germanium semiconductor.
So this is the last part, which is the reference part. We provide four main references for this report. The first one is Donald A. Nieman, 1982, Semiconductor Physics and Devices, published by MC Grow Hill Education. The second references is Resistivity Measurement on Germanium for Transistors, published by Semantic Scholar. And then the third one is the Solid State Electronic Devices, the 7th edition, that published by Pearson. And lastly, the Introduction to Solid State Physics, 8th edition, that published by Wiley. And this is the main references that we use for our analysis, question and answer, discussion, and also conclusion throughout this experiment.